All right. So then. Okay. So how's the seminar been? How's the webinar been going? I think I saw there were some very good speakers on there.
Yes, so it's going fine actually. So
it's a very international lineup, right? So.
Yes, and we get active participation. A lot of questions sometimes we got.
I see. I see. Actually, okay, should I just share my screen and see if it works? Yeah. No. Okay, share. Okay.
See,
Hopefully we can see everything okay.
Yes, but it is not in full screen.
Yeah. Wait just a second. Here we go. Okay, is that now on full screen?
But I think it's not in that way. It's showing the behind whatever you have also. So I think it's not in the presentation mode finally.
Right. No, I'm trying to leave a part on the side where I can write something.
Oh, okay.
Okay, but I'm not sure how I can get rid of this table of contents here. Here we go. That's better.
So you can change one slide. Can you just check that it's okay perfectly?
Of course. So we're here and.
Okay. Okay. So I think it's perfect.
Okay.
Okay. So.
Well, by the way, so how much time should I speak? Is it 50 minutes or?
Yes, 50 minutes is fine.
Okay. Okay. Just want to make sure I don't go over. So if we start at, I guess yes, now it'll be, I guess.
We will start.
Okay.
Okay. So on behalf of the organizers, a very warm welcome to Professor Aurik Shah and all participants of the webinar on PDE and related areas. For the participant, we request to store your questions in the question answer box. We are honored to have Professor Aurik Shah with us today. Professor Shah obtained a doctorate under Professor Sergio Kleinerman at Princeton University, USA in 2010. Currently, he is a senior lecturer in the School of Mathematical Sciences at Queen Mary University of London, UK, where he is an integral part of the Geometry and Analysis group. He is the undergraduate student exam board chair in Queen Mary University of London, 2020. His research areas are partial differential equations, in fact, dispersive, hyperbolic, and wave equations, differential geometry, mathematical general relativity, in fact, Riemannian and Lorentzian geometry, geometric PDE, Einstein equations, and control theory. He has publications in prestigious journals like Journal of European Mathematical Society, Journal of Functionalities, Advances in Mathematics, etc. He has been awarded EPSRC First Grant 2018 to 2020 and awarded the Special Mention of Research Contribution in 2018. A lot of study material is provided on his webpage. I suggest students to have a look at his webpage. Today, he will be speaking on controllability of waves and geometric Carleman estimate. I hope you will enjoy the talk thoroughly. Professor Shah, it's over to you now.
Thank you. Yeah, well, let me, of course, begin by thanking the organizers for this invitation. So I think this is the first time I've spoken in India, even if I can't actually go at this time, unfortunately. But it's a huge honor to still to be able to speak at the webinar. And also thank you for the very nice introduction as well. Okay, so today I wanted to speak a little bit about this area of research that I've been working on for the past couple of years or so, right? And this is on the control theory and controllability of waves. And so I've been working on well, this is a very well-known and very familiar problem probably to some of you, but I've been working on this from a slightly different perspective, a more geometric perspective than I think what most of the standard literature is tends to have. And so I want to share with you some of the more recent results, as well as kind of where I would like to go with this. Okay, so I'd like to, I guess, for the first third or so of the talk, I want to give a bit of an introduction and really of a survey of what control theory is, at least in the context of wave equations, and what the standard results in literature are, before we talk about what I'm doing. Okay, so let me begin first with wave equations, right? And so I guess this is just setting notations. I think most people hopefully have already seen what the wave operator is. So here I'm going to use this box symbol here just to mean the usual wave operator, right? And there's different sign conventions that people use, but here I will take this wave operator to be minus dt squared and then plus the Laplacian here in the spatial variables x. Okay. And I'll write these on this board on the right-hand side, just so we'll remember. Okay, so besides just the standard wave operator, we also want to look at other linear wave operators, say with some lower order terms, right? And so throughout the talk, I'll call this the script L, and this will just be the wave operator, this box, and you have a first derivative term, so a derivative in some x direction and some derivative in some capital V direction, right? And so here, this capital V and this capital X you can think of as potential and as the first order coefficients of this more linear operator. And then here we keep in mind that both X and V depend on both T and X. So they're time dependent and space dependent coefficients. Okay, and just a little bit of a justification of why we study wave equations, right? And so wave equations one can think of as one of the simplest examples of hyperbolic PDEs. And moreover, they're also present in many fundamental equations of physics, right? For example, if you look at the Euler equations that study you have fluid flow, right? There one can actually find wave equations or wave type equations hidden within these fluid equations. Also, if you look at the Maxwell equations from electromagnetism, right? These very clearly contain wave equations within. And then one that has had more press recently is the Einstein equations for studying gravity, right? And so there's been many recent discoveries of gravitational waves, right? And these were predicted about 100 years ago, long before we had the equipment to detect these things, mainly because people discovered that there were wave equations hidden within the Einstein field equations of relativity, right? And so just to make the point that these are very physical PDEs. Okay, so one bit of a very basic background is what when we can solve wave equations, right? And so here for this talk, we're mainly interested in wave equations, say, posed on bounded domains, right? And so for now, I'm going to take a spatial domain, this capital Omega. This will be an open subset of Rn, say with a smooth boundary. And then also for our system, we also pick what I call the initial final time, so t minus and capital T plus. And so then what we want to do is we want to solve the wave equation on this finite cylinder, right? On the spatial domain omega, and then from time t minus to time t plus, right? And the wave equation will solve, at least in general, will be L of phi. So L is as we wrote before, and then we may possibly have some forcing term F on the right-hand side. Okay. And for this particular problem, well, we know from basic undergraduate or basic postgraduate maths that one generally has a unique solution called this phi, as long as you're given initial data, say at the initial time t minus, along with boundary data. So you can either pose the Dirichlet or the Neumann boundary data on the side, right, on the whole time across the boundary. Okay, so then that's right. So if you want to solve the wave equation, that's very much a well, it's going to very much be seen as a passive observational approach, right? So you're setting the initial conditions and you're just letting your system go and you're seeing what happens to the system, right? So here, what we're more interested in is this question of control, which is a bit more of an engineering or more proactive approach, right? So rather than just sitting back and seeing what happens to the solution, we want to be more active and see, can we make the solution what we want it to be, right? So can we control what happens to our solution? Say, if you're given the initial state of the system, then can we achieve some desired final state of the system? Okay. So now the unfortunate part is that if we're in any real world situation, then we don't have unlimited powers. We can't just say, here, a system become this at this time, right? We can't just tell it to do something and have it do exactly that, right? And so the problem is that we can only directly affect some subset of the system, right? This part that we call the control, right? I think the most simplest example is if you're driving a car, you can't just put a car somewhere. You can only turn the steering wheel and push 2 or 3 pedals. So we have very limited ways to control our system. Okay, so now going back to the more abstract mathematical picture, right? So then what are the standard limited ways that we can affect our system? So usually when we study these things mathematically, then there are 2 different classes of controls that people consider. Right? The first one is what's called boundary control. And this is where we steer the solution phi through boundary data, right? So in here, we're solving the homogeneous equation, L of phi is equal to 0. And we pick some subsets, gamma, of the side boundary. And then what we want to do is we want to basically use either the Dirichlet or the Neumann boundary data posed on this subset, gamma, as your control to try to drive the system to whatever state you want it to be. Okay, so that's one way to do this. And another way that's also very often studied is what's called interior control. Right? And so rather than doing this through the boundary term, then one wishes to steer the solution through a forcing term, right? So here we want to solve L of phi is equal to some function g, right? Where this g is now might be supported only on some subset of your domain. Okay. And so here, just to not complicate things too much, I'm going to focus pretty much the entire talk on the problem of Dirichlet boundary control. Right? So we're going to use the Dirichlet data on the boundary of our domain as the control for our system. Okay, with this in mind, then I can now state the problem of it's a precise problem for control, and this is what's called exact controllability. Right, so here again, we set our control region to be some subset gamma of our boundary. And so the question we want to ask is, well, given some initial data and some final data, which we'll call phi 0, phi 1 plus and minus, so minus being the initial data and then plus being the final data, right? And you don't have to worry about the spaces. This is just technical detail here, right? And so what we want to do is we want to find a function, say, call this phi sub d on the boundary, right? This can be thought of as a Dirichlet boundary data, right? Such that if you solve the wave equation, L of phi is equal to 0 on this finite cylinder, with your given initial data, so phi 0 minus phi 1 minus at the initial time t minus, as well as your Dirichlet boundary data that you want to find, then the system will have exactly the final data you want. Right? So the state of the system at the informal way of writing this is, can solutions be controlled, fully controlled, using just the Dirichlet boundary data? Okay, so there's a couple of observations here that's special to wave type equations, right? And the first one is that one can, without any loss of generality, take either the initial data or the final data to be 0. This is what's one is often refers to as null controllability. Right? And the reason that we can do this comes from the fact that the wave equation is time reversible, right? That we can solve this forward or backwards in time. Right? So one can always add or subtract a solution of the wave equation with 0 boundary data. And you have an equivalent problem. Okay, so because of this, from now on in the, for most of the theoretical discussion, I'll always assume that the initial data is 0. And this is just to make sure that some operators I'll talk about are linear. Okay, the second main observation is that is a property of a wave and hyperbolic PDEs known as finite speed of propagation. Right? And this is just the fact that solutions of wave equations travel at finite speed. Right? And so the consequence of this is that if you have any information that you impose on the boundary through your control, then this information needs some finite non-zero time to travel to the interior of the domain. And so this implies that there is a fundamental bound on your time span, the difference between your final and initial times, in order to be able to fully control your system. Okay, I guess this is so there's kind of many ways to describe how one solves this control problem. So here, let me give one method that's really a bit outdated, but I think it's the most elementary way to see how this all works, right? And so this is a bit of basic postgraduate functional analysis, right? And so here, what we do is we consider this linear operator S, right? And you don't have to worry about the spaces if you don't, if you like. This is just the spaces you need for the formal theory. Okay, so this operator S, then this takes a function on your subset of the boundary, right, where you're putting the control, right, and it maps to some state, right? And so what this S does, right? So essentially, what it does is that you're feeding in some boundary data, phi of d, that's supported in this gamma, and then what you do is you solve the wave equation, the homogeneous wave equation, L of phi is equal to 0, and you solve it with 0 initial data, and your boundary data being this phi d that you're given. And so then if you solve this equation, then this operator S essentially it outputs back to you the state of your solution at the final time, t plus. Okay, so that's, here's just the operator S that just solves the system and then gives you back the state of your system at time t plus. Right, and so now if you think back to the definition of what it means to be exactly controllable, right, you want to kind of make sure that you can achieve every possible final state given as long as you start from the 0 initial state, right? And so this problem of exact controllability is equivalent to showing that this operator S has a full range. Okay, and so then from a bit of functional analysis, we can consider the adjoint of this operator S, right? And if you sit down and you do the computation for about 5 minutes, you can see what the adjoint of this operator is, right? And so what the adjoint essentially does is that it amounts to solving backwards the adjoint PDE. Okay, so this L star of C is equal to 0. Right? In particular, you feed into this operator S star the final state of the adjoint system. So this C0 plus C0 1, and you solve this adjoint wave equation with this final state, C0 plus P0, C1 plus at time t, and you impose 0 Dirichlet data on the boundary. Okay? And then what this operator outputs back to you is the Neumann trace of your solution on the boundary. Okay, so those are the operators, and so now if you again go back to some basic functional analysis theorems, you know that about duality and what's known as a closed range theorem, then again controllable or being exactly controllable is equivalent to this first operator S being surjective, and then by the closed range theorem, this is equivalent to the adjoint S star being injective, along with this linear bound that I write here. Right, and so now if you write out this linear bound for the adjoint operator S star, then what you get is what is known as the observability inequality. Right? That if you the energy norm, the H1 cross L2 norm of your solution of the adjoint wave equation at the final time is bounded by its Neumann trace at the boundary on the subset gamma. And again, just to remind, here we're for this adjoint wave equation, we're imposing 0 Dirichlet data. So let me, this comes in quite a bit, so let me just write this down. Here, and so this is just say this is at final time is bounded by the Neumann choice. Okay, so that's what's known as the observability inequality, at least for the wave equation with Dirichlet boundary data. And so because of this equivalence, then in this control theory, then the main goal is usually just to prove this observability inequality. Right? Because once you have that, then you can invoke, say, this functional analysis machinery to give a positive answer to the exact controllability question. And of course, I can't talk about controllability and observability without mentioning Lyon. And so basically, his contribution is what's known as the Hilbert uniqueness method. And so this is essentially the modern machinery for going between observability and controllability. And so on top of just kind of answering the question of exact controllability, this machinery also allows you to generate the control that you want, this phi of d, in particular, for example, as a minimizer of a functional. And then moreover, one can also, via this method, find the control that minimizes, say, the L2 norm on the boundary. Okay, so let me finish this this introductory part by just talking a little bit about the main methods people have used to prove the observability estimates and hence solve the controllability problem. Right. So the first method is what are known as Fourier. Is known as Fourier series methods, right? And so these this method in general applies to special wave equations in one spatial dimension, right? Say of this form. And so the idea here is to apply Ingham's inequality or variance of that on the solution, on the Fourier expansion of the solution. Right? And so here I just wrote Ingham's inequality here just for reference, but I won't be speaking of the Fourier method again. So I think this is all I'm going to say about this. Okay, the second class of methods is what's known as multiplier methods. Right? And so here this applies to the free wave equation, this box of C is equal to 0. And the basic idea here is to start with this identity you see here, that this integral of a box psi times this multiplier s star of psi, and this s star will just be some first order operator applied to psi. Right? This is of course equal to 0 because box of psi is 0. Okay, and the idea here is just to take this integral expression and to start integrating this by parts, right? And you see what you get. And if you do this carefully enough, then what you get is this following theorem, right? So here one fixes some reference point. We'll call this x0 or x0 in Rn, and we assume this this bound on the time span, right? Again, one needs some lower bound on the time span, and so here let me write this down. Right, so the lower bound we need is this thing here. So you need that the time span is bigger than 2 times sup of the boundary, and then x minus x naught. And so the way that you can interpret this is that you can think of this at least the right hand side here, right? So this this absolute value you can think of as the distance between your reference point and any point on the boundary, right? And so what this says is that the amount of time span you need is at least the amount of time you need for any information from the boundary to reach the reference point x0, and then to go from x0 back to the boundary, right? And that's where the factor of 2 comes from. Okay, so then given this lower bound on the time span, then the result is that for just the free wave operator, one has observability, and then with the domain gamma, the subset of the boundary being precisely the entire time interval, and then points on the spatial boundary, partial omega, satisfying this inequality. Okay, so I guess one can interpret this inequality quite geometrically, right? And so the way to do this is given by this picture I drew on the slide, right? So one essentially just draws an array from the reference point x0 to the point on the boundary that you want to think about, right? And so essentially this point on the boundary is in this gamma as long as this ray is leaving your domain omega at that point. Right, so here in this picture on the blue point here, this ray, this arrow in green, is leaving the domain. So then this blue point is in this set gamma, whereas this purple point, at this purple point, this arrow is now entering the region, right? And so then this is not in this set gamma. So I'll put this down, put down this formula on the right-hand side because I will refer back to this a bit more in some later slides. Okay, so the next class of methods I want to mention, and this is one that I'll talk about for the remainder of the talk, is what's known as Carleman estimates, right? And so I think this is what's acknowledged right now as the most robust technique in the sense that it applies to the largest amount, the largest class of differential operators, right? And so in particular, this extends the result from multiplier methods to general wave operators with lower order terms. And so essentially in about a third of the slide, what is a Carleman estimate? And so these are essentially weighted space-time integral estimates with an extra free real parameter, right? And so here I gave kind of a schematic statement of what a Carleman estimate would look like, right? So here on the left-hand side, you're essentially controlling the H1 norm of the solution psi, right? And along with this extra weight, e to the lambda f. And on the right-hand side, you have a box of psi, as well as possibly some boundary terms that we'll discuss a bit later. Right? And then in this estimate, besides this weight, e to the lambda f, one also has this free parameter lambda that's large, right? And so the idea here is that one can, well, if you solve a wave equation, then you can replace this box of psi on the right-hand side with lower order terms, right? And now, because of this free parameter lambda, if you take lambda to be large enough, then this term here on the right-hand side can now be absorbed into the left, right? And this gives you a way to kind of treat these lower order terms in the linear waiver operator. And so the upshot of all of this is that the previous theorem from the multiplier methods also hold for general operators L of the form that's again written on the right-hand side. But now there is this one kind of stupid technical shortcoming, which is that for all the classical Carleman results, one also requires this condition that this reference point x naught lies outside our domain omega, right? And this is a bit of a technical limitation, but it does restrict the ability to study some control domains on the boundary. So, okay, I'll come back to that a bit, but it's a side point and it's a bit technical.
Actually, in this point, there is a question that can we take the reference point x naught inside the domain or on the boundary? What are the
yes,
difficulty may appear?
I see. I think as far as kind of all the results I've seen in literature, then no. But with the results that I'm talking about today, then yes, we do have a way of putting x naught inside. Okay. But that's I looked for a long time for past results in other papers that allow you to do this, and I could never find it. So that's kind of something that's kind of one technical thing that's also an improvement over previous results. Okay, and lastly, of course, I have to mention microlocal methods, just because microlocal analysis has been very, very influential in the study of controllability for wave equations, right? And so in particular, this method gives the most precise and the optimal results, optimal with respect to the size of the control region. Okay. But in order to get these optimal results, one has to pay a price. In particular, one has to assume that the coefficients, the lower order coefficients of x and v of our waiver operator are also analytic in time or independent of t. Okay, so this pretty severely limits the class of equations that we can consider. But here the optimal result is the following: is that you have observability on the subset gamma of the boundary, if and only if this gamma satisfies what's called the geometric control condition, or GCC, right? And this is the statement that every bicharacteristic within your domain will hit this subset gamma of the boundary at least once. Okay, and this is under the additional caveat that these bicharacteristics will reflect off the boundary via geometric optics laws. Okay. And then there's a more recent results from for French authors that also expand this result to also consider subsets gamma of the boundary that are time dependent as well. Okay, so again, these microlocal methods give the optimal results, essentially that given by the geometric control condition, right? But it doesn't treat as many operators as one can via Carleman estimates. In particular, one has the additional restriction that x and v must be analytic in time. Okay, so that's essentially all I want to say about the introductory part and the survey. So before I go on, maybe I'll stop and ask if anyone has any questions. Okay, if not, then I can go on to the next part. Okay, so with all the introductory stuff done, then the main question I want to ask is, well, again, the same problem, but now what if we consider time-dependent domains, right? And so these are domains whose shape can change over time, right? And so here, instead of just taking a time interval across a fixed spatial domain omega, we now allow the spatial domain to also depend on time, right? So here we have this omega sub tau, which represents this changing spatial domain as you increase in time. And so then U is just kind of the union of all these omega slash taus put together. Right. And so in particular, our space-time domain U now has a moving boundary. Right. And this is this U sub B here that I write in the middle of the slide. Right? And this boundary, so this side boundary can change its shape as you change in time. And the main question we want to ask is, well, given this time-dependent domain, can we still prove similar exact controllability results for the wave equation? Okay. And again, the only other fundamental assumption we have to make here is that this side boundary UB is what's called time-like. And so this is a bit of terminology from relativity, but essentially what this means is that if you look at the boundary UB, then it's changing at less than the wave or the characteristic speed. Right? And so essentially what this tells you is that this boundary is appropriate for imposing boundary data. Okay, so then kind of given this domain, then one can ask exactly the same question that we had before for controllability, right? So you're given now some subset, say script y of the boundary, and then again, our goal is to find for any initial and final data, you want to find some boundary, some seriously boundary data phi d supported on the subset y that takes your solution phi from the initial state to your final state. Right, so this is exactly analogous to the exact controllability problem I stated earlier, but just now for a time-dependent domain. Okay, and now if you can run this new system through the exact same machinery that I described before, namely this Hilbert uniqueness method, then we see that the exact controllability, this question of exact controllability is again equivalent to this question of observability for the adjoint system, right? And again, this is a question of controlling the energy of your system at, say, the final time t plus by the Neumann trace on the subset y given zero Dirichlet data. Okay. Right, and so then for everything that we're doing from here on, the goal is to prove this observability inequality. Okay, so what has been done for this problem, right? And so while there's been many results for the time-independent domains, the existing literature for time-dependent domains is actually quite sparse, right? And so one thing I can mention for this is that these microlocal methods won't work, or at least we don't know how to make the microlocal methods work for this time-dependent problem, right? And this is, I guess, one way to think of this is that you can given this moving boundary, one can change coordinates to straighten out the boundary, right? But at the cost of turning a wave equation into some other hyperbolic PDE, right? And so now your hyperbolic PDE is going to be very time dependent, right? And in general, not in a time analytic way, right? And so because you're not, because your PDE is no longer time analytic, then these microlocal methods, at least for now, are out of the question. Okay, so now what has been done? So for general dimensions, I think the only results I've seen are for the free wave equation. So when L is equal to just box, right? And so there's the old results of Bartels and Shen from the 80s, right? And this applies to the case when your domain U is expanding in time, right? And so there you have an extra decay in your energy estimates, and you can kind of use stabilization methods to solve this question. And then another set of results comes from Miranda in the 90s, and so this they look at the case when the U is what's called self-similar. So this is essentially the case when your spatial domain at any time is some dilation of some fixed domain. And then moreover, this U is asymptotically cylindrical in the sense that it's asymptotically as t goes to infinity. It's becoming more and more like just a static time-independent cylinder. Okay, so those are the results that I know for general dimensions. And then in recent years, there's been various works in one spatial dimension. Again, these also use the multiplier method and apply only to the free wave equation. And so these consider the case when the boundary of your domain is given by two lines, so one vertical line and one slanted line. Or there's some results in which one can, where the boundary is given by a vertical line plus some time-like curve. Okay, these are very clumsily drawn on the right-hand side of the slide. And there's been various authors that have done this in the past, say 5 or 7 years. All right, so what's missing from this picture is essentially a general results in any dimension. Okay, so at this point, then I can give an informal statement of the main result that I want to talk about, right? And so this is published last year, right? So here we're going to look at a general wave operator with general lower order terms, this L, on this moving domain U, right, without any restrictions. Okay, and so then the rest of this terminology you'll find kind of familiar from what we've discussed. So we fix some reference point x naught, which has the same purpose as what I've written in the right-hand side here. And we again assume this, this lower bound on the time span t plus minus t minus, right? And so, and now this is now bigger than r plus r minus, where r plus r minus are given by these formulas you see here, right? And this has essentially the same interpretation as before, right? So you want to give yourself enough time for any information from the boundary at the initial time to reach this point x naught, and then to go from x naught back to the boundary at the final time. Right? That's the interpretation for this lower bound. Okay, so then given this restriction, we then have an observability estimate. This is written here, right? So you can control the energy of your system at, say, some time. That this is bounded by the Neumann trace of your solution on the subset Y. And moreover, this observation region Y, which is actually a time-dependent set, and it's much smaller than what you would get from classical methods. Okay? I'm just going to put this rather vaguely for now. I think later on, as we discuss the proof of the results, I can explain better what I mean by much smaller. Okay. And then, of course, from this observability result, the corollary of this is that one has exact controllability for this wave equation with control imposed on this region Y. Okay, a couple of remarks, right? So as far as I know, this is the first result. The first result that treats this time-dependent domain problem for general domains U, and also for general wave operators L, right? And so, and then moreover, on top of this, if you look at kind of this theorem in the special case of time-independent domains, right, then this actually improves upon the existing Carleman or multiplier results that's available in the literature, in the sense that one requires a smaller control domain than before. And then I guess going back to a question that was asked earlier, then for this result, one can now put this reference point x naught either inside or outside the domain. Right? This is, as far as I know, a new thing for at least for Carleman type results. Okay. So now one area where this falls short in comparison to the microlocal methods is that this in general does not achieve the geometric control condition, which is the optimal type result. One can only get the optimal results in terms of the control region when you're looking at one spatial dimension. Okay. The second set of remarks I want to make is that one has proven one has similar results for the problem of interior controllability, where we impose the control on on the forcing term on the inside of the domain. And this was done recently by my PhD student. In a recent paper that just came out a few months ago about Vebov, right? So I think he has connections to some people here as well. So so I certainly want to advertise some of his recent work, which has been very nice, right? And okay, and so there's been it's actually been a bit more difficult than anticipated, right? So there's kind of two separate parts. One part for static domains, for time-independent domains, but more regular controls, and then the second part that's in preparation for time-dependent domains, but less regular controls, right? And actually, what's a bit surprising is that the part that already comes out is actually much more difficult to do than the part that's kind of currently in production, right? And so somehow kind of achieving this more regular control requires a lot more technical work. There's various reasons behind that I won't have time to get into now, but the paper is on arXiv. Okay, so I guess what I want to do for almost the rest of the talk is to say a bit about the proof of this result, which I guess still haven't stated completely precisely. Okay, but I want to break this down into three parts, which I hope are a bit more digestible. Right, so the first part, we want to just focus on how one achieves these results for time-dependent domains, right? And so to do this, we'll just restrict our attention to the model problem of the free wave equation. So we're just taking L to just be box without the lower order terms, right? And this allows us to apply multiplier methods, right? Which simplifies a lot of the technical stuff, but it can still kind of show how we deal with time-dependent domains. And then for the second part of this proof, we'll see how we go from the free wave operator to more general wave operators. This comes from establishing the Carleman estimates. Right? And so this is essentially a discussion on how one proves the Carleman estimates. And then the last part, we'll if there's time, probably not. I can say a few things about how one goes from the Carleman estimates to the observability estimate. And this is a somewhat standard process, though with a few new tricks as far as the case when X naught is inside the domain. Okay, so before I start the proof, maybe I'll ask again if there are any questions.
I think we have questions, but I think we will take at the end, maybe after your presentation. There are certain we have certain questions, but I think there are lots, so I think we will take at the end.
Okay, that's fine. That's fine. In that case, I'll just keep pushing. Okay, so let me start with the first part. And so let's for this, let's again restrict our attention to the free wave equation. So L is just equal to box. Right, and so for this, I have to say just a little bit more about how the multiplier result works. Right, and so here again, we start with this formula here on the first equation of the slide, right? And moreover, I can say that that this first order multiplier we take is given by what's on the right hand side here. So this x, this multiplier s s star 0 of psi is given by this first order. So you have this radial of essentially RDR of psi, and then plus this constant times psi. So you take this this integral here, and you start integrating by parts, and you do kind of a lot of these integrating by parts, and then you apply this with the conservation of energy for this free wave equation. And if you do this carefully enough, then what you get is this inequality. Right? So you have this t plus minus t minus times the energy of the of your solution, which the energy is again just the h1 dot cross L2 norm, the standard one when you study wave equations. Then this is bounded by 2r times the energy on the right hand side, plus this boundary term. Right, and so the key observations that you want to make from this inequality, first of all, if you look at the green parts, right? So now if t plus minus t minus is strictly greater than 2 times r, then this energy term on the right hand side can be absorbed into the left right? And so in particular, you control the energy by this boundary term, right? Which is what the observability estimate looks like. Okay, the second observation comes from this part in orange, right? And so this x minus x naught dot, this nu, which is the outward pointing normal to the boundary, right? So in particular, here we only have to look at the part when this orange part is positive, right? Because whenever the orange part is negative, then the integral over that portion of the boundary will be negative, and you can just drop that from the inequality. Okay, and this in particular gives us the control region, right? Okay, so that's how the classical multiplier method works. And so now this comes, we can ask, well, how does, and why does this cause trouble in the time-dependent setting, right? And the main issues is that, first of all, the conservation of energy no longer holds. And so that's going to cause some trouble in what we're doing. And then moreover, if you do integrations by parts and energy estimates, if you don't do them the right way, you're going to get a lot of extra boundary terms coming from the moving boundary. Okay, so how do we kind of deal with this and how to explain this in, say, 2 slides, right? And so I guess the first idea is to kind of view this this problem a bit more geometrically, right? And not just that, but also in terms of the geometry of the full space-time R cross R1 plus n, rather than just the geometry of the spatial part, right? And so this is inspired by the mathematics behind special relativity, right? Where we kind of put, in particular, when we look at this what's called Minkowski space-time, right? And so this is again an R1 cross R, and then as the metric which defines the geometry is what looks like the Euclidean metric on R1 plus n, except that we flip the sign of the time component. Okay. And so this, in particular, this is the geometry behind special relativity in physics, but also this is the geometry that's naturally associated to the wave operator, right? And that's why it's highly useful in studying wave equations. Okay, and then the second kind of point here is that whereas the previous classical multiplier results relied on this reference point x naught, here we want to replace this notion of this reference point by a reference event, right? So we don't only have this point x naught in space, but also a fixed reference time t naught as well. Okay, and then kind of with that in mind, the second thing is that we want to modify this this multiplier as follows, right? So here we add this extra term containing the time derivative of psi to our multiplier, right? And so now we have the classical multiplier we had before plus this extra time derivative term, right? And so and this principal part of the operator actually has a lot of connections to the geometry of the wave operator as well. I won't get into that here. This is something one often sees in other facets of studying the wave equation. But for now, let me just mention that this extra term in the operator, kind of where that comes in, technically speaking, is that this corresponds, if you kind of look at the extra computations arising from this term, then these essentially correspond to the energy conservation arguments that we had in the classical multiplier arguments. Okay, and then the last idea is that we want to apply the integration by parts, kind of not so much the usual integration by parts, but actually integration by parts with respect to the Minkowski metric. Okay, and so what this means in practice is that one gets a slightly different outward pointing unit normal to the side boundary, right? And this is what's called the Minkowski unit normal, which is essentially just the Euclidean normal that you would get using the usual Stokes theorem, except that you reverse the sign of the t component. This comes from the metric. Okay, and the point is that if you kind of treat the entire space-time geometrically, right, then having kind of these curved boundaries no longer scares you, right? Because you can just apply the geometric Stokes theorem there, and that deals with all these moving boundaries automatically. Okay, so now if you put all these things together, then I guess what you get is this is the improved version of the multiplier result, right? And so I think most of this is the same as before, right? So you have we restrict to the free wave equation, and we have the same lower bound on the time span, and then we essentially get this following observability estimate, right? The only new part coming here is I tell you what the subset of the boundary is, right? And so in particular, this is the part of the boundary that satisfies this inequality, this Minkowski normal applied to this function f naught is positive, right? And so then what is f naught? F naught is essentially x minus x naught squared minus t minus t naught squared. So I'll say a bit more about this function a bit later on. Okay, and then T naught is chosen kind of to satisfy these two inequalities, and this can always be done as long as this lower bound on the time span exists. Okay, a couple of remarks is that the proof is actually embarrassingly easy. It takes about 2 pages if you write it out. Right? It's extremely simple, right? But it's also quite powerful, right? If you look at the case of one spatial dimensions, then this already recovers all the existing results in the literature and in full generality, right? And in particular, you can get the optimal time span, the one from the geometric control condition for all such domains. And then for the general N, then this will handle general domains U, and you won't achieve the optimal time span necessarily. But in general, you will get a much smaller time span, a much smaller time span than you would from the previous results in the literature. Okay, and then finally, let me mention that this condition, this n of f0 is bigger than 0, that defines the control domain. Right, this can be thought of as a generalization of the one that we previously got from multiplier methods. Okay. And namely, if you look at the case when the domain U is time independent, then these two conditions are exactly the same. And if you're looking at the case when U is expanding away from time t naught, then your Y that you need, you can think of as being slightly smaller than what you get from the classical situation. And then if U is contracting from P naught, you need a slightly larger control region. Okay, so I think I'm rapidly running out of time, so I'll try to go very quickly through the Carleman estimates and wrap up there, because I think I'm already about supposed to stop. Okay, so I'll try to say as few things as possible for the Carleman estimates, right? So here we want to, so we've taken care of, or at least explained a bit of how you deal with moving boundaries, and so now we want to address the question of how do we deal with general operators L with general lower order terms. And again, we want to establish a global Carleman estimate of the following form. And so again, you're controlling the H1 norm by box on the right-hand side, and then plus some boundary term that will be the right-hand side of the observability estimate. And so if you want to break this down into kind of one step, then one can think of this as starting with this integral that I wrote at the bottom of the slide, and then integrating that by parts. Right, and if you've got to parse what this means, this is essentially a multiplier estimate for the wave operator conjugated with this weight e to the lambda f, and then for this I guess renormalized c given by this weight times c. Okay, so I think the most important thing that I can tell you about this Carleman estimate is essentially, what is the Carleman? What is this weight e to the lambda f? Okay, and so for this, I will have to, I guess, lie to you just a little bit about this, but and I can maybe say just a little bit at the very end of kind of why a bit later of kind of what the actual correct weight is. But here I just want to at least to demonstrate the concepts. I want to tell you something that's not quite true. Right, so what's not quite true is that the weight is constructed from this function f0 that I mentioned before, just listing here, right? In particular, if you and then you can define this weight to be f0 as this lambda power times this exponential that we're not so concerned about. Okay, so a bit of basic properties is that if you look at the level sets of f0, then these are hyperboloids. Well, if you look at f0 is equal to 0, then this is just this double null cone about the point t0, x0. And then if you look at the positive level sets of f0, then these are the one-sheeted hyperboloids in the, and then I'll call kind of the script d0 to be the set of all points where f0 is positive. And so this is just the exterior, the outside of this cone here. Okay, so the important feature here is that if you look at this weight, e to the lambda f that I mentioned before, then this weight itself naturally vanishes at f equals 0, which is again just the double cone, right? And so what this tells you is that if you integrate the parts as you derive this Carleman estimate, then you do not get a boundary term at all at f is equal to 0. Right, and what this allows us to do is this allows us to basically get an estimate that's supported entirely on the outside of the null cone, without any boundary terms on the cone itself. Right, and so then this essentially allows us to get the Carleman estimate here, and this looks like what I wrote before, except that everything, all the domains, are now restricted to this d0, this exterior of the cone. Okay, and so then from here you can do the usual energy inequalities, and this will give you an observability estimate now with this y, right? And so this y is essentially what we had before, except we now have this additional restriction to the null cone exterior, this d0, right? And this is precisely the improvement in the control region that I mentioned in the main result, right? And if you look at the classical Carleman methods, then what you get is essentially kind of this y here, but without this extra restriction. Okay, so this is precisely the gain that you get. Okay, and okay, maybe this is a nice place to kind of. Okay, so this gives us some nice pictures of what's going on. Okay, right. So here, this left cylinder here, this is essentially the boundary of our moving of our time-dependent domain. Right, and so in the second picture here, we look at the case when this t naught x naught, our reference event, is inside the domain. Okay, and then in this case, the control region that we get this y is essentially just this green part here, right? The intersection of the boundary with the exterior of the null cone. That's what you'll get for the control region. Okay, now for the last two pictures here, we will look at the case when t naught x naught is outside the domain. And so here in the third picture, you have this purple part is once again the intersection of the boundary with the outside of this cone. But now in this case, not every point on this boundary will satisfy this condition n is f, this condition n of f is bigger than 0, right? And so in fact, only this green part of this portion will satisfy that inequality, right? And so then the control region you get here is what's shaded in green in the last picture. Okay, I'm rapidly running out of time, so let me just finish this talk in like one minute, in 1 or 2 minutes, right? And so I guess the last thing I'll tell you is that is kind of why I was lying to you before, right? So I mentioned a couple slides ago that this Carleman weight is constructed from this function f0, which gives you these hyperboloids. Okay, and Okay, and so this doesn't quite work, and the reason is if you've kind of studied Carleman estimates and unique continuation theory, then you know that the main requirement for Carleman estimates is this property known as specific convexity. Right, I won't have any time to discuss what exactly that is, but let me just suffice it to say that if you look at the level sets of this function f0, then it just barely fails to be pseudo-convex. And the consequence of this failure to be pseudo-convex is that you can only derive a degenerate Carleman estimate in which you control the L2 norm of your solution, but not the full H1 norm. Okay, but if you don't have the H1 norm, then you don't have observability. And so for this purpose, you don't have what you want. Okay, and so then the upshot is that one cannot build this weight from F0. Okay, and so the idea is that you have to perturb the weight a little bit into something that is pseudo-convex. Right, and if I had time, I would have talked a little bit about kind of how one perturbs this F0 into something that is pseudo-convex, but I'll just say that it is quite a bit different than what's done in the classical Carleman literature. It uses a little bit of conformal geometry, but I won't talk about that now because I'm already late. Okay. These last two slides are a few technical points on how you go from the Carleman estimate to observability. This is mostly standard, except for the part when T0, X0 lies in the boundary, but that's somewhat technical. So, okay, let me just finish with the precise statement of the main observability estimate, which is the main results, which I think most of this is the same as what I mentioned before. The only new thing is now I can give a precise statement of what the control region, what the observation region is, right? And so this is actually any open subset of the boundary that's just slightly larger than what we had before. Okay, and the reason that you get the slight loss, that you need y to be slightly larger than this region that we discussed before, this is just because of the fact that we perturbed this F0 into a slightly different function, right? This accounts for the slight loss, but this loss can be arbitrarily small because we can make this perturbation to be arbitrarily small as well. Okay. Okay, and then so just to conclude, right? So again, the main results here is that we proved controllability for wave equations on time-dependent domains. And again, this is, as far as I know, the first general result that applies to general domains and operators. And it's also, as far as I know, the best known results using Carleman estimate methods, in the sense that it requires a smaller control region than before, and it gets even improved results for time-independent domains. Okay, and then finally, I should mention this as well, that the proof uses entirely geometric ideas and intuitions, and this kind of gives the possibility of using these geometric ideas, to also study geometric wave equations, right? And that is the topic of ongoing work that I'm doing with Webov. Right? This is extending these tools to also kind of treat the controllability problem for hyperbolic equations or wave equations, or for wave equations with time-dependent geometries as well. That's something that's completely unexplored in the literature. Okay, so I'm already way over time, so let me just stop here and thank you for your attention.
So, thank you, Ori, for such a wonderful talk. So we have received some questions. Okay. So I am conveying to you on behalf of that. So there are questions in the question answer box, also in chat box. So maybe I will just read for the chat box first. Okay. What happens if the boundary has a corner? What would be the observability estimate and GCC condition in that case? Or you don't allow any corner over the time period?
Yeah. Corners, right? So, okay. So I think, as far as the GCC, it gets quite a bit tricky, right? As far as how you define the reflection conditions, right? So that's a little bit tricky, I think. I don't want to give a precise answer for that just because I'm not sure. Right? But there are ways to define, to kind of generalize the GCC to corners. As far as these multiplier / Carleman methods, I think these corners don't bother you so much, right? Because I think these integration by parts and these Stokes theorems, they apply to domains with piecewise smooth boundaries. And so I think for these Carleman type methods, these corners generally don't bother you nearly as much.
So another question is, if you have some damping term, do you expect better estimate? And if you have potential as a lower order term, will it be possible to say anything about the scattered waves caused by it?
Okay, so as far as if you have a damping term, then you would have better energy estimates for sure, right? You would have decay in the energy, right? As long as you have enough damping, right? As far as observability, I don't think it affects kind of. I don't think it fundamentally affects the exact controllability result as far as what domains you need. Right? I mean, what it does affect is if you look at the observability estimate, then that will affect the constant of this that you kind of see that you get in the observability estimate. Right? I think if you have energy decay, that's going to make this constant much smaller. But it's not going to affect the region Y so much.
Okay. So there are other questions in the question answer box. So in the Carleman estimate, we generally take the exponential weight function. Is there other type of weight function that works?
Well, I mean, so the exponential isn't so much, it's more a convenience than it is kind of something essential, right? It's basically it's just saying that your weight is positive, right? If you have a positive weight to some power, then you can write this as e to the lambda something, right? So there's nothing kind of particularly essential about the exponential. That's positive.
So there is another question. The 4 methods you mentioned are for the linear wave equation. What
Yes.
about the nonlinear wave equation?
Ooh, okay, so there's there's various ways of studying the nonlinear wave equation, right? So I think one, some of which I'm familiar with, some of which I'm not at all. So I don't want to comment too much on that. But I think one elementary way of attacking the nonlinear wave equation is by applying one of these linear methods and then doing some iteration using some fixed point theorem to generate the control. I think there's been quite a lot of literature over the past 30 years that have at least tackled wave equations with some very weak nonlinearities. Right, but that's can be a much trickier question, just because if you have a nonlinear wave equation, then you have blow up. Right, your solution may not exist for a certain amount of time. Right, and moreover, because of finite speed of propagation, here for this control problem, right, even if you impose boundary data, you may not be able to stop the blow up. Right, this data you put on the boundary may not affect your system fast enough to stop your solution from behaving badly or no longer existing. Right, and so that becomes a lot trickier. But again, one can do iterations. That's one possible method. There's many other ones.
So the other two are construction of control is also important from the economical point of view. What are the methods available in the literature for construction of the control of wave, linear or nonlinear equation?
Okay. Okay, so I'm less familiar with the nonlinear just because I think there's much less results there. By the way, so I can also mention for nonlinear wave equations, right? So one of the advantages of Carleman estimate methods is that they don't require your coefficients to be analytic, right? And so this kind of and so in the results on linear operators using Carleman estimates, I think there's more potential for that to be kind of used for iteration type arguments for nonlinear wave equations. Okay, so then as far as controls, right? So what you mentioned is a much well, okay. So there's the general method I know for constructing controls, right? So it's this idea from the uniqueness method, in which one basically can formulate the control as a minimizer of some linear functional, right? And so that you can kind of try to do that maybe computationally or so on. Right? There's various variational methods for getting to that. You know, as far as kind of what computer algorithms are generally used on the computational side, that I'm kind of less knowledgeable about. But at least on the theoretical side, you can formulate this this minimal control, the one that minimizes this norm, as a minimizer of some positive functional. Okay. Of course, for many real world problems, right? So here we're not really putting any kind of restriction on the control, right? It's just anything in L2, right? Of course, for any real world problems, you probably also have some other restrictions or constraints on what controls are achievable, right? And so that's kind of something that's not covered by this basic theory. Right? And so let me kind of close that question by saying that there's still a lot of mathematics that could be done here. Some very basic mathematics.
So there is a question that what can you say about the controllability of a system of wave equation? What about the case where the coefficients depends on the space and time? So it's for a system of wave equations.
Okay. Well, okay. So there's kind of two separate questions hidden in there, right? So if you have a system of wave equations, as long as the principal part is of every component of the system, right, is just this box, right? So basically, every component is a wave with the same speed. Okay, and as long as you have the common speed, then everything I mentioned here, as far as the Carleman estimate and so on, right, everything applies to this system of wave equations. You can probably also do better, right? So I haven't kind of done this with these new methods myself, but I know that there's results in the literature for systems of wave equations that you can also kind of have this Carleman condition that you would see for the finite dimensional systems, right? Where you also have this gain from being able to transfer information from different components of on the boundary. So you don't necessarily need to put. You may only need to put controls on some portion of the on some subset of your unknowns, right? And there's some Carleman type condition that kind of tells you which ones you need to impose controls on, right? So I think I'm sure that with a bit of work you can combine these methods that I mentioned here with kind of these Carleman type things that have been done in the literature. You can get kind of, results in that fashion. I hope that wasn't very clear, but I hope that answered it somehow.
Okay, so are you telling that if for the system case, if you put the control on the both components in the boundary, then your method will work?
Yeah, right. That will work immediately.
Okay, but if it is on one component, you are not sure.
I mean, that depends on the algebraic kind of, and that depends on your system now. Right, there's if you look at the case of ODEs, right, then you have to look at how the system couples.
Okay.
Right, and so you have similar conditions here as well.
So now I ask the participants if they have some more questions, so they can raise their hand or they can write it, and then otherwise I will have two questions.
Okay. So I can't see that. I'm sharing the screen right now, so I can't see that. I'm not sure where to see the chat at the moment. But feel free to ask anyway. Oh, here we go.
Okay. So then I have the questions in the context that you have told that about the exact controllability of the wave equations. So now my point is, we are here, the time plays the role, that is T is greater than that. So suppose you are considering the approximate controllability.
Mhm.
In that case, what is the role of the time? Will you get optimal time for your case with the variable coefficients?
Yeah. So I mean, so as far as kind of wave equations are concerned, I think I don't know. There's too many situations where you have approximate controllability without exact controllability.
Yes.
So I think these are the cases where you have a unit continuation result from the boundary, but not observability.
Yes.
Right. And I think, usually as long as you kind of give yourself enough to get a unique, well, okay. So, I mean, there is a regime that where you might have one but not the other, but it's but that's a pretty kind of small and pretty strange one. But I think the counterexamples to just unique continuation without observability is that's very tricky. It's many open questions there. Right. So so I think it's okay. So as far as kind of this I mean, I don't think kind of having the time dependent domain kind of affects this regime that's between approximate and exact controllability in any fundamental way. Right? So I think kind of things that are in between these two things is probably the same in the time dependent case as it is in time independent case.
And if you have a system case, in that time to prove the unique continuation, will you use some kind of a Holmgren? That kind of Holmgrens are available when you have a system case?
I mean, from what I'm interested in studying here, no, just because here we're assuming that X and V are not analytic in any way. Yes. Right. Of course, if X and V are time analytic, right, then yeah, I guess you have this Tataru result, which kind of does the usual Hormander, these Carleman, this Hormander in the spatial directions, and then Holmgren in the time directions, and that gets you a better unique continuation result.
But that is for a single wave equation, right? Not for a system of wave.
I think it also holds for systems as well, right? As long as it has the same principal part, and all the coefficients are time analytic. I think that the Carleman estimate, at least, and has unique continuation. Right? That is that generalizes directly to systems. It's a very different story if all your components of the wave have different speeds. Right? Then I think it becomes much trickier.
In that when you have a variable coefficient, in that time, do you have a control cost or the observability estimate, the constant, how it depends on time, or you have any prescribed information?
Yes, yeah. So actually, in the results in my paper, I do give an estimate on the constant of the observability, right? And so I think the constant I get is completely analogous to the ones I think there's a paper of who was it? I think Zhuozhuo Song and Duquert, I think there they compute some constants, and I think we get the same kind of constants as there. So I don't think this. The short answer is that these constants you get are kind of very exponential in the radius, and it's completely analogous to what you get for the time independent case.
Okay. So, and so this is another question related to the nonlinear wave. So if you have a nonlinearity corresponding to the wave equation, so do you have kind of a restriction, any restriction on time that is for optimal, anything is known? For a nonlinear wave equation, the time of controllability, optimal time of controllability?
Okay, that I'm not much less sure about. I think for the nonlinear equations, there's much more fundamental constraints, right? I think if you want to get exact controllability even in the first place, right, then I think you have to, you're looking at kind of a pretty ridiculously restricted class of nonlinearities. You can only look at, I think, box of phi is equal to phi times natural log. of natural log squared of phi or something like this, right? It's a very, very restricted class, right? And this is just because, if you put, box of phi is equal to phi squared, right? Something that's a bit more natural, then you can always have blow up, or at least in some cases you can have blow up, right? And your control may not be kind of strong enough to prevent that, right? And so I think, as long as you have this blow up, then there is no exact controllability question, at least the full question.
Because I asked this question related to that, for one dimension case, if your nonlinearity is there, and then you can reach steady states under certain conditions.
Yes.
So the question comes that, okay, what about the other states? So in the proof of the work of Coulomb, they have constructed a control so that you can reach steady states. But it is not known at first, as far as I know, that what are the states you can reach outside steady states. At least the time is large enough if it is given.
Let's see. Yeah, I mean, that I'm not sure about. I think that there's a lot of things that are unexplored there, right? I think I didn't really mention this during the talk, but I think this is kind of something that I hope that my that these methods that I use that just kind of don't require any analyticity can help to study.
And you obtain in the case what is the regularity of the control in this case?
L2.
L2 control.
Yeah. So it's the usual.
Okay.
Yeah. But here, I guess the main point is that you can look at I guess in the paper I assumed x and v to be these low order coefficients to be smooth, but really these can be like C1 or something like this. They're much more restricted, C1, C0. Okay. And so there's hope for kind of using kind of these Carleman methods to do some kind of iteration argument to study exactly kind of this question you mentioned.
And from the as you show the work of interior control corresponding to Vaibhav, so from interior to boundary, the extension method doesn't work in this case.
I mean, there's a regularity issue, right? And so I guess it's a bit of a right. So what's caused so much trouble in the interior control case? It depends on what space you want to put your control, right? And so if you want to, if you're solving the wave equation with the forcing term, right? Then the usual way to do this is in the energy, is in H1 cross L2, and then the forcing term then some L2 base space, right? And so this is on the observability side, right? And so if you do this, then you're going to get a control. Then your control is going to be in some very, very irregular distribution space, right? Whereas if you want to, sorry, I said that completely wrong. Sorry. Right. So if you want to impose the control in the forcing term, right, this is going to be in some L2 base space, right? Then if you're doing observability, then you have to get a Carleman estimate in the L2 cross H1 regimes in this very irregular regime. Right, and that becomes very, very tricky to do, right? It's so if you right, so it's not just a matter of doing an extension from the boundary to the interior, but also kind of getting these estimates in a much less regular space. That's kind of where the trouble comes from, right? I think as far as extending to the doing extension arguments, I think that part is that works just fine as far as I know.
So thank you, Auric. So I thanks again all the participants and Auric for this wonderful talk. And so if there are no more questions, let us thank the speaker once again. We meet on Tuesday for the talk of Professor Guila Casto on fractional Michael-Simon-Sobolev inequalities. Till then, I think we can stop now. So
thank you again.
So I request the participants to leave the platform now. So thank you, Auric.
Okay.
So,
thank you.
Thank you.
Cheers. Stop sharing screen. All right. Well, let me thank you again for the invitation. It was very nice.
Thank you. So you see some new things actually, at least for time-dependent domain.
Yeah. So, and there's before I go, I think you worked with WebOff before you came to Queen Mary, right?
Yes, with Boiva. Yes.
Yeah. Okay,
Yes,
so
yes.
he's doing very well. He's currently working on this geometric problem. So
Okay. Yeah, no, he sent me that he has one work already.
yeah.
Yes.
No, he did the work on the interior control, and I mean, I originally gave him that problem as a warm-up problem, but it actually ended up being much more difficult because of this regularity issue.
Oh, okay.
So you had to do a lot of kind of pretty intense technical things to kind of get through that. So which is a bit unfortunate, but that also means that he's done something quite interesting. Okay, no, okay, I remember having that connection.
Yes.
Yeah. Okay, very good.
Okay.
Well, thanks again for the invitation, and hopefully I can meet you in person sometime. So.
Yes, sure.
All right. Okay. See you.
Bye.
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 Oops.